Monotonicity means same behavior. It means like we say, it is very monotonous. Monotonous means it is of the same tone, or there is no change, there's no variation. So monotonicity in functions is referring to its increasing nature or decreasing nature of functions. A function is monotonically increasing or monotonically decreasing. So we apply that for increasing nature or decreasing nature. So for example, y equal to x is a graph, we know, is a straight line like this. Y equal to x, it is a monotonically increasing function. All right, it increases. Whereas y equal to minus x is a monotonically decreasing function. Simplest of examples. Monotonically increasing function, and this is a monotonically decreasing function. Now, this has a bearing on maxima and minima. It's very important. Now, increasing and decreasing nature, very important is we move from left to right on the x-axis. When we are moving from left to right, that means we are moving towards increasing values of x on the x-axis. Then if the function value is increasing, then it is monotonically increasing. And if the function value is decreasing, then it is monotonically decreasing. It is not the other way. If you go from right to left, it shows other ways. But we are not doing that. We are going from left to right. Now, how do we define this monotonic nature? So what is an increasing function? Increasing function. Now, if for all x1 and x2 belonging to the domain of f, I'll write D, each time I'll not write domain. If for all x1 and x2 belonging to the domain of f, if, okay, for x1 less than x2 implies or double implies that f of x1 is less than f of x2, then f is said to be strictly increasing function. It is said to be strictly increasing function. That means, look at the graph. Very simple way of explaining. Now, x1 is a smaller number, x2 is a larger number. Function value at x2 is larger than function value of x1 at x1. Now, no matter what, x1 and x2 can keep changing throughout the domain. But if the function value of a greater number is greater than as compared to the lesser number, then it is an increasing function and it is strictly increasing. Now, but if for x1 less than x2, the double implication is f of x1 is less than or equal to f of x2. That means the function values of 2 points can be equal. They can increase and then they can be equal also. For example, let's take this function. Okay, this is a function. On this region, there are function values at 2 points which are equal. Or in fact, in this whole region between x1 and x2, this is constant value. It's a now such a function, then f is said to be increasing. We don't call it strictly increasing. We say increasing or non-decreasing. Okay. Now, this is the fundamental definition. Now, we'll use this in derivatives. So in derivatives, f dash x is limit h tending to 0, f of x plus h minus f of x upon h. H is a positive quantity. Now, if x plus h is greater than f of x plus h is greater than f of x, it means it is an increasing function. For suppose this is an increasing function, x plus h is greater than x, so f of x plus h will be greater than f of x. So it is limit h tending to 0, a positive value by a positive value. So the derivative will be greater than 0. The derivative will be greater than 0. So definition using derivative. So if a function is continuous and differentiable in its domain and f dash x is greater than or equal to 0 for all x belonging to the domain, and f dash x equal to 0 only at isolated points, then f is said to be strictly increasing. So we have seen here that f dash x greater than 0 means it's an increasing function, the slope. Now, sometimes it so happens that at some isolated points, f dash x can be equal to 0. So, for example, y equal to x cube. Let us take this example. This is a very important example to understand monotonicity. So here we see, so this is the function f of x equal to x cube. The derivative is 3x square and the derivative becomes 0 only at x equal to 0 and nowhere else. So at x equal to 0, you get a horizontal tangent. But for all other x, the derivative is always positive. So this equal to 0 is only at one point, an isolated point. It is not over an interval. The previous graph that I showed here, this one, the function is function value, the derivative is 0 over this interval because you have a horizontal line. Over the entire interval, it is 0. So this is not strictly increasing, whereas this is a strictly increasing function. So we should not get under the impression. Of course, f dash x greater than 0 throughout, it is a strictly increasing function. But f dash x greater than or equal to 0 is also strictly increasing as long as f dash x is 0 only at isolated points. This is an example for it. So based on this, now decreasing function, we can similarly write for decreasing function. For decreasing function, so if for all x1 comma x2 belonging to the domain x1 less than x2 implies or double implies f of x1 is greater than f of x2, then function is strictly decreasing. Function is strictly decreasing. So what we get, f of x1 is greater than f of x2. So function is a decreasing function. All right. Now it need not be strictly decreasing. We can get a case like this where the function is like this, constant in between, and again like this. Then it may not be strictly decreasing. But however, in using derivatives, when we define again, if f dash x is less than 0, then it's a strictly decreasing function. So just take this minus x cube, the graph changes. This is the graph. So there's a strictly decreasing function. So at any given point, you see the tangent will have a negative inclination throughout. Only at one point, at x equal to 0, the derivative will be 0. But all other points, the tangents will have negative slope. So function is decreasing. That means when we are moving from left to right across x-axis, the value of the function is decreasing. Okay. In this case, when we move from left to right, the value of the function is increasing. Now, a function can be increasing for a while and decreasing for a while. Isn't it? Our graphs of sin x and cos x are like that. Now, these are not, you cannot say they are strictly increasing functions or decreasing functions. These are increasing on a certain interval and decreasing on a certain interval. So sin x, the graph of sin x, it's an increasing function on, you see, minus pi by 2 to pi by 2, it increases. In this region, it increases. And then pi by 2 to 3 pi by 2, it decreases. So 2k pi minus pi by 2 to 2k pi plus pi by 2. Sin x is increasing for every periodic, its periodicity. Period is 2 pi. So you keep adding 2 pi. For every that interval, the sin x will be increasing, and it is decreasing for, or we should say decreasing, okay, decreasing for the interval 2k pi plus pi by 2 and 2k pi plus 3 pi by 2. So these functions, we say they are monotonically increasing in a particular specified interval only. It is not throughout. Okay. So this is about monotonicity. And this is very useful in graphing. When we do curve tracing, this is something extremely important. A function may be increasing or decreasing, but its curvature, you see the curvature, this is, concave up. It is concave portion is upwards. Here there is no curvature, it's a straight line. And here there's a curvature which is concave is down, or the convex portion is up. So what makes the difference? So here you see f of x1 and f of x2. F of x2 is greater than f of x1, where x2 is greater than x1. Now, because we can see the function is increasing, so when you move from left to right, the first derivative is 0. The first derivative is 0. Now look very carefully. At x1, I draw a tangent. At x1, I draw a tangent, and at x2 also I am drawing a tangent. Whose slope is greater? The tangent at x2. The inclination is greater with the x-axis, so the slope will be greater. What is slope? Slope is the derivative. So f dash x gives us the slope. So now what is happening is, now when you study these slopes, when you move from left to right on the x-axis, the slope value for this function is increasing as we move from left to right. So in this case, f dash x is an increasing function. In the first case I'm talking about. So if f dash x is increasing function, then its derivative must be greater than 0. So you get that the second derivative is greater than 0. So when we get second derivative greater than 0, we get a curvature in the curve which is such that the concave portion faces upward. Just like first derivative means it tells about the tangent, it has positive slope. So just by seeing this curve, we can say, okay, this is, increasing function. The first derivative is positive. At any point you take, the first derivative is positive, right? Similarly, if you have a curvature with concave facing upwards, it means that the second derivative is positive. Whereas now look here, this is an increasing function, but f dash x is a constant. F dash x is positive, but is a constant here, because there's a line, f of x is a straight line. So first derivative will be a constant. All right, it is of a constant slope. So second derivative will be 0. So when second derivative is 0 means the curve will not have a curvature, at least at that point. But here throughout second derivative is 0 throughout. So it's a straight line. Understood? And here this is an increasing function. We can see if I draw a tangent here, at x1 I'm drawing a tangent. This is the tangent, and x2 I'm drawing a tangent. Now the slope of the tangent at x1 is higher than the slope of the tangent at x2. So as I'm moving from left to right, my slopes f dash values are decreasing. So in this particular case here now, for this case, f dash x is a decreasing function. This is a decreasing function. So what we get here is f double dash x will be negative. All right. F dash x will be negative. Now, same concept. Let us look for decreasing functions. Decreasing functions, it is very clear. Function is decreasing. At every point, f dash x will be negative, negative, negative. No problem. We know that. You see the tangent here. It's having a negative slope, negative slope, negative slope, negative slope. Okay. So tangents have a negative slope. So this is a decreasing function. As we move from left to right on x-axis, the function is decreasing. So first derivative will be negative. But then you see here, okay, this inclination is closer to y-axis and it is the negative inclination. All right. And this inclination, this line, tangent line is, more inclined towards the x-axis. So what will be the value? This will be close to, say, minus infinity, and this will be a negative value but close to 0. So the values of the slope are changing from some large negative number. I should not say large negative number, numerically large, but with a negative number. So it is a small number. Minus 100 is much smaller than minus 1. All right. So the slope is changing from a numerically large negative value to a numerically small negative value. So actually the values are increasing. So f dash x is an increasing function. Therefore, f double dash x will be positive. In this case, f dash x is negative and its slope will be equal throughout, and therefore the second derivative, because f dash x is a constant, the second derivative will be 0. And here in this case, we see the slope is a number close to 0 and this is close to minus infinity. So when you move from left to right, the values are changing from, say, minus 2, minus 3, minus 5, minus 10, minus 100, so on. So the values are decreasing. So f double dash x, so f dash x is a decreasing function. So f double dash x will be negative. So this is the conceptual understanding of why second derivative is greater than 0 or less than 0. But now, notwithstanding all this, so in both the cases, what we get is this. In both the cases, what we get is, if second derivative is positive, it means the curve is concave upward in curvature. So while tracing the curves, this is very important. How will the graph be? Will it be positive upwards? Will it concave upwards or concave downwards? We have to see. So whether it is increasing or decreasing, as long as the second derivative is positive, it is concave up. Whether it is increasing or decreasing, as long as the second derivative is 0, it's a straight line, increasing or decreasing. And whether it is increasing function or decreasing function, if second derivative is negative, concave portion is facing downwards and convex portion is facing upwards. This is the nature of curvatures. This will be extremely useful in curve tracing. All right, we will discuss this again just before finding the areas and the curves, but this is a very important part of monotonicity and finding monotonic functions, and its use in finding maxima and minima.